Okay, you guys, so let's go ahead and now take a look at integrated rate law. Hopefully this video will work. This is maybe the 7th time I'm trying. Okay, so integrated rate law here. Remember that the main feature is that instead of having concentration and rate, we're provided with information of concentration and time. So you can always recognize integrated rate law problems because they include the variable time. Either they're asking you to solve for time or they provide you with time. And remember that the integrated rate law, the actual rate law itself, is written in the form y equals mx plus b. We'll look at that a little bit more closely in a second. But they are a little bit more complicated than the differentiated rate law, which is in the form of rate equals k times concentrations. If the problem just asks you what is the rate law, you can write either the integrated or the differentiated. If it says what is the integrated rate law, you have to make sure that you write the integrated rate law. So we're going to use graphical analysis to determine, I'm not sure why my pen's not working great, to determine what order the reaction is in. Remember that we can only apply integrated rate law when only one reactant is part of the rate law, or when we are only given information about one reactant. When I say graphical analysis, I mean we actually have to graph the data. If you don't know how to graph on your calculator yet, because we did go over that in class, you should definitely let me know so I can teach you how to do that again. But to be fair, in AP problems, they do normally provide you with graphs these days, so they don't actually expect you to graph. Instead, they provide you with the graphs. So we have 3 options here. If our graph of concentration versus time is linear, then we know it's 0 order. If our graph of natural log or ln of concentration versus time is linear, then we know it's first order. And if our graph of the reciprocal or 1 over concentration versus time is linear, then we know that it's second order. Okay. When we identify the order, saying that the graph of, for example, natural log of x over versus time is linear is enough explanation. So you don't have to give a further explanation for how you knew the order. The order is based on which graph provides the linear line. Please note the slope of these lines. The 0 order and the first order graphs do have that negative slope, whereas the second order graph does have that positive slope, and that's going to be important when it comes to K. So I think we need to look real quick. Let me just go ahead and grab, I think I can do this. Excellent. So I think I can grab this here. Let me try to make it bigger so that you can see it. Okay, so we can take a look at, these are just straight from our notes from class. You know, we have 0 order, first order, and second order reactions. We just talked about this first row here, plot that gives the linear line. That's repetitive. Plot that gives a straight line is what we're trying to say there. Obviously, if it's a linear, it's straight. So we know that. From there, we know the differentiated rate law. Because we've identified the order and it's only one reactant, we know that rate is equal to K for 0 order, because that would have been concentration of A to the 0, which is 1. We know that for first order, it's going to be the rate is equal to K times just the concentration, because again, it's like there's a little 1 right over here above the concentration. I'm not sure if that mark is showing up. There we go. Like a 1 right there. So that's first order. And then second order, of course, is going to be rate equals K concentration squared. So that's the differentiated rate law. So if they just ask me for rate law, cool, I know it. I don't need to do anything more. However, most likely in an integrated rate law problem, they might ask you to solve for at what time. And to solve a problem for at what time, or a problem like what will be the concentration at this specific time. So a problem that involves time, we're going to need the integrated rate law. Remember, we talked a lot about this in class, that the integrated rate laws, while they seem complicated, they are literally just the equation in form y equals mx plus b. So for example, for the zero order reaction, since our y-axis is concentration of A, we see concentration of A right here. And then it equals mx. On our x-axis, we have time. And our m, our slope, is going to be our k value. And you'll see that there's a negative right there because we talked about the slope. I think I can show you here. The slope right here being negative, right? So there's that. Okay, so that's y equals mx plus b. The B is the initial concentration. So this is the concentration at time equals 0. Normally that point is provided to you in the chart that's given to start the problem. And then we can just go across the row. We do exactly the same thing. If our graph is natural log of A, then we have y is natural log of A. And this is going to be the natural log of A at time equals 0. Again, we have that negative sign because that graph has the negative slope. Right over here, for the second order reactions, you can see it's the reciprocal. We don't need the negative here because our graph actually has a positive slope already. The k value should always be positive. The k value should always be positive. And then the intercept. So there's that. The next column here just talks about the slope, remembering that we have to throw that negative in front for the first and zero and first order graphs. Okay. The next is the units. So if you want, you can just memorize the units of k based on the order, or you could just use the differentiated rate law to solve for the units, like we would in the previous video about differentiated rate law. So I normally opt to solve for my units every time, but if you prefer to memorize them, you're welcome to. Just be aware here, this little note, that it could be any unit of time. Very often my students lose points because they automatically use seconds, but the data provided to them might be in minutes or hours or something like that. And then the last piece here is about half-life. Okay, and so half-life is the amount of time, so half-life should always be in a unit of time, the amount of time that it takes for half of whatever substance we have to be used up. These are the equations. I pointed out in class that our equation sheet has a first order time half-life reaction, a first order half-life equation is what I'm trying to say on it. And so that to me indicates that if they ask me to solve for half-life, it's probably going to be first order. But technically we should be able to calculate something for zero order or second order. And this is going to be super easy because by the time we try to solve for half-life, we probably have already calculated K and they've provided us with the initial concentrations. This 0.693 number, I think it gets calculated somehow using the natural log or the E, really, the E value. But we don't need to be able to derive that equation. The thing is with half-life is it's important to understand what half-life means, because sometimes students miss this, especially on multiple choice. So for example, let's say there's something that's like 2 molar, okay? And you know that the half-life is maybe, let's say, 3 seconds, okay? I'm just making this up. So 2 molar is what you're starting with, and the half-life is 3 seconds. They might ask you, how long will it take for it to be like 0.125 molar? So they're asking you, how long is it going to take to be 0.125 molar? I find that if you write out these problems, it will help a lot. And if you don't write it out, you're normally going to be off by 1 cycle. So what I mean is, like, I'm going to say, okay, I'll start with 2 molar. If half of that gets used up, it becomes 1 molar. Okay, if half of that gets used up, it'll become 0.5 molar. Notice that it's half of whatever remains, okay? And then if half of this gets used up, it's going to be 0.25 molar. And then if half of that gets used up, ooh, now I'm at 0.125 molar. So this took 3 seconds. This took 3 seconds. This took 3 seconds. And this took 3 seconds. So total, it's going to take 12 seconds for this to happen. Okay. Drawing it out graphically like this will always help to ensure that you have the correct number of half-lives that will have surpassed. So that should help there. And that is a super common multiple choice question that I see in some form. Okay. All right. So let's see, just making the list with integrated rate law. They're going to ask us what order. They're going to ask us to write the rate law. They're going to ask us to solve for K. Okay, now solving for K, remember, probably means finding the slope of the straight line. Normally, we don't plug into the rate law and solve for K. The way we solve for K is finding the slope of the straight line, and then be sure to remember to think about if you need to throw a negative in front of that slope to make the K value positive. Remember, the K value should always be reported as a positive value. Be sure to specify that. Okay, so this is going to be finding the slope of the straight line. Make sure K is positive. Okay, and then also include the correct units, which you can solve for if that's easy for you, or you can memorize it from right here. Okay. All right, cool. Include correct units, solve for K. Next thing they might ask you to do is either they'll give you a concentration and ask for time. So you would just plug into the y equals mx plus b equation and solve for t. Okay, or they could give time and ask for a concentration, right? Either way, we're just using the integrated rate law, which would be like right here, okay? Integrated rate law, and we would plug in the values until we either solved for T or concentration, okay? You wanna just be careful here. We had a problem where they might include stoichiometry. Some stoich, right? They might include some stoich here. So just be ready for that. And again, you could do factor label type stoich, or you could do BCA type stoich, whatever is useful to you. And then the last thing is, oh my gosh, what's happening? Don't stop working. My video is gonna stop. What do? I don't even know how to use this properly. Well, I'm just going to tell you that the last thing that might come up is that, close. Okay, the last thing that might come up is, shoot, now I forgot what I was going to say, you guys. Oh, half-life. And we already talked about half-life. I haven't normally seen too many reaction mechanisms with this unless it was a combined, differentiated, and integrated problem. All right, I think I'm going to be out of time here, so I'm going to go ahead and stop this video if I know how. That's questionable. It might still be recording. Just me like figuring this out.